As we think about the kernel further, again, the kernel is all the points that map through that linear transform always to the zero vector in our output space. When we've looked at a few examples, we find out that the kernel isn't just some set. It's not some arbitrary set. It actually has some nice structure to it. And specifically, that it's highly structured and probably something like a vector subspace. So we're going to identify that. Imagine V and W are two real vector spaces. Then the kernel is going to be a vector subspace of V, of the input space. So that's a key. The input space. So all the inputs that map to 0. This is what we're interested in. Now, just to remember, what are the requirements for a subset to be a vector subspace, and not just some random collection of points or vectors, but this structured element? We have those three classic definition points. The zero vector, and careful of the input space, so the input 0, has to be an element of the set S here. S must be closed under addition. And thinking ahead, S must be closed under what other condition? Scalar multiplication. And I hope you can feel there's a connection here. Remember, this is a linear transform, so it has special properties about, scalar multiplication and addition. So it feels like when things map to the same. Anyway, we're going to tease this out, but it shouldn't come as a huge shock that we're having the theorem that we have here. So first, recall what the kernel is. The kernel of some transform is a set of vectors, let's call them V's, from our capital V set, such that when we transform them, those V's become the zero vector in our output space. And again, just a quick Venn diagram here. We have our W space here, we have our V space here, we have specifically the zero vector in W. And what we're claiming is the points that map to 0 are not just scattered, but they are somehow related to each other through a vector subspace relationship. So the kernel is all these points here that through L map to the 0 vector. And if we're going to try to prove those three properties, well, let's start with number 1. Our question is L of the 0 vector from our input space equal to the 0 vector from our output space? In fact, we did show this a little bit earlier, that this is guaranteed for a linear transform, but we can do a quick verification here just to reassure ourselves again. If we consider the linearity property, that L of alpha V is equal to alpha L of V, then with alpha equals 0, the L of 0 times our vector V, and that's going backwards, that is the transform of the 0 vector in V, because whenever we take 0 scalar times any vector in our space, then we're going to get the 0 vector in our input space. This linearity property, though, lets us bring the 0 outside, and this is some vector V, sorry, this is some vector W in our output space. So we took some random point here, we mapped it to some random point here, but then we're going to multiply it by 0, and that definitely gives us the 0 vector in the W space, because 0 scalar times any vector gives us the 0 vector in the output space. So 0 vector in V maps the 0 vector in W, so the 0 vector in V is an element of the kernel of L. Somewhere in here, we have the 0 vector in V, and it is always going to map to the 0 vector in W, no matter what. Next up, condition 2, closed under addition. So the routine for this is the same as always. We consider two elements of the kernel. So we're going to call them V1, V2, because V are the input values or input vectors. So take two vectors in the kernel of L, and that means that we know that the transform of V1 is the 0 vector in W, and the transform of V2 is also the 0 vector in W, because that's the membership condition for being in the kernel. Well, our next step is to ask, is V1 plus V2 also in the kernel of L? Well, let's take a look. What would this mean? i.e., is L of v1 plus v2 equal to the 0 vector in W? That would be our test for being in the kernel. Well, let's consider L of v1 plus v2. Well, remember we have our function, and it is a linear function. So this is equal to L of v1 plus L of v2 by the linearity of L. That's one of our fundamental properties for linear transforms. And this is the 0 vector in W, and that's the 0 vector in W as well. Why? Well, because these two things here are exactly the relationships that made the first vectors into the kernel, and we add the 0 vector to itself, we get the 0 vector back as well. And that means that v1 plus v2 is also in the kernel of L. When we transform these two vectors added together through a transform, we also get the 0 vector back. So going back to our diagram here for a second, if I take any two vectors in this red line here and I add them together, I'm also going to get something that transforms through L to the 0 vector. So there's that commonality. And last but not least, we're going to look at the feature of whether it's closed under scalar multiplication. Specifically, is the kernel of L closed under scalar multiplication? And for that, we're going to need to consider a V in our input set, which is the kernel of L, and some alpha that's real. So we're going to take these, and our question is the transform of alpha times V in the kernel of L, i.e., is the transform of alpha V equal to the 0 vector in W? Well, again, think back to what we know here. We know, because V is in the kernel of L, that means that the transform of V is the 0 vector in W. So we're going to look at the transform of alpha V. That's what we're asking. And well, that is equal to alpha times L of V. Why? Because that transform is linear. By the linearity of L, we know this is true. But now we've isolated L of V by itself. Well, we know that is the 0 vector in W. And we also know that if we take the 0 vector times any scalar, we get the 0 vector again. And that means that L of alpha V is the 0 vector in W2. So L of alpha V is in the kernel of L. It gets mapped to the 0 vector 2. And so we've shown that the kernel of L, that set of input values that we get that map to the 0 vector, stays the same if we scalar multiply. Any element in here, if we scalar multiply, it also still maps to the 0 vector. And so finally, because 1, 2, and 3 as our criteria, we're all satisfied. The kernel of L is a vector subspace, or just a subspace, of the input set, or the input space V. Perfect. So that's something that we can use as a fact, especially when we're trying to figure out things like, hey, what dimension is the kernel? Well, the question about dimensionality only makes sense if we're talking about a vector subspace, and now we know we can use that kind of terminology for this kernel.